Okay, this is the lecture number 5, and it is about the introduction to stiffness method for beams. So this method, in this lecture, we will discuss the stiffness method for beams in quite detail. We will be covering these topics in this lecture today. First, we will introduce this stiffness method. Then we will extend this introduction to a stepwise procedure for beams, and then we will review the kinematic indeterminacy, and then we will ending up with the example problem number 1 and example problem number 2. Okay, so now let's start with the introduction to the stiffness method. The stiffness method is also called the displacement method. We call stiffness method a displacement method also, and it is also one of the primary method in matrix analysis. We did study flexibility method in previous lectures. So matrix analysis actually consists of two methods. One is the flexibility method, and the other is the basically it consists of flexibility method and stiffness method. So we covered the flexibility method, so now we will be covering the stiffness method. One of the advantage of the stiffness method over the flexibility method is that it is very conducive to computer programming. Now, if you remember, in the flexibility method, there were certain steps in which the input from the user or the decision from the user was involved. For example, in the very first step, if you remember, in the flexibility method, we were required to select the redundant actions. So a computer cannot select the redundant actions for you. So it means that in the flexibility method, the computer, if you leave everything to the computer cannot solve the whole flexibility method in just one go, because it requires the decision of the user at various steps. But in the stiffness method, it is easy for computer programming, because there are no such human decisions involved. There is a straightforward method. You just need to code that method in computer, and then computer will start. And whenever you start that program, that computer program, so computer will then take the inputs and it will give you the output, right? So if you remember, in the previous method there were engineering decisions involved, but now in this method they will not be required once the analytical model of the structure is defined. Analytical model means that once you define the geometry of the structure, once you define the material of the structure, so once the computer program know that what is the dimension of the beam or frame, or what is the loading type, and where is the loading type acting, and what is the EI value or EA value, so then there is no further engineering decision involved in the stiffness method. So that's why it is very easy for programming. So you can this programming is not the it is not the part of this course of structural analysis 2, but in future, when you will be dealing in the field, so every time you cannot just sit and take your pen and start doing it manually. You should develop some programs for yourself, so with which you can efficiently solve the problems in the field, right? So that's why I have included this advantage of the stiffness method over here. Okay. Okay. So now, in the flexibility method, in the flexibility method, the unknown quantities are the redundant actions. If you remember, in the flexibility method, the very first step was to select the to find out the static indeterminacy of the beams or frames or trusses, and then depending on the degree of static indeterminacy, we were required to choose the redundant actions, because there were many actions in the structure, but we were required to select 1, 2, or 3 or more redundant actions as per the degree of static indeterminacy. So depending on if one student is solving a beam on flexibility method, he may choose some actions as redundant actions, and the other student, if he is solving, so he may choose some other actions as redundant actions, as you may have seen in the assignment which I've given to you. So different students have taken different actions as redundant actions. So that's why in the flexibility method, the redundant actions are arbitrarily chosen. Okay, they are arbitrarily chosen. You can choose any actions as redundant actions. There is no compulsion involved, right? So you can choose any actions. That's why a choice is involved. Whereas in the stiffness method, the unknowns are the joint displacements. The unknowns are joint displacement, and that's why this is called this is also called a displacement method, because the unknowns are the joint displacements. Whereas the flexibility method is also called force method, because the unknowns are the forces, the actions, okay, in the structure. So now in the stiffness method, the unknowns are the joint displacements. And what do we mean by joint displacements? The joint displacement can be a translation, it can be a translation in the x-axis, it can be a translation in the y-axis, or it can be a rotation if you're talking about a 2D member. So it means that the unknowns, as these are the joint displacement in the structure, so they are automatically specified. They are automatically specified. You don't need to choose them, because if there is a beam in which there is a hinge support, so we automatically know that there will be a rotation at that end of the beam where the support is hinged. Whereas if there is a fixed support, so we automatically know that there is no displacement at the fixed support. There is no translation, there is no rotation involved. So we don't need to choose this. This is automatically specified, okay? This is automatically specified. Okay, so now in the stiffness method, the number of unknowns, which are the displacements, they are to be calculated. They are equal to the degree of kinematic indeterminacy. Okay, so it means the very first step will be to find out the degree of kinematic indeterminacy. What is kinematic indeterminacy? Kinematic indeterminacy tells us about the degree of freedom. Okay, it tells us about the degree of freedom. It tells us that which joint has how many degree of freedoms. Okay, so it tells us about that whether a joint is translating under the load, or whether it will be rotating under the load. So by finding the degree of kinematic indeterminacy, we will be able to find the number of unknowns, as the number of unknowns are the joint displacements. Okay, so now let's now clear this concept through an example. This will also be a stepwise procedure here. So this is introduction. Also, this is the stepwise procedure. So we will be then applying the same steps later on the problems. So you need to be very carefully listening to all this. I'll be going very slow, and then in the problems we will be speeding up. Okay. So now we consider a beam. We consider this beam, and you can see that we have a fixed support at A, and we have a roller support at B. This is just an example beam. Okay, we want to clear the concept of the stiffness method through this example. So this is the beam, and this beam is acted by this uniformly distributed load of magnitude W. Okay, so this is the length. The length of the beam is shown by L. Now, if you look at this beam, you don't need to choose the displacements. You don't need to choose the displacements, because we know that the joint displacements, the possible joint displacements are 3 at this fixed end, and also they are 3 at this end. But the property of the fixed support is that it restrains all these 3 displacements. It don't allow the beam at this end to translate in the x-axis, or to translate in the y-axis, or to rotate. It means that there is 0 number of displacements at this fixed support. There are 0 displacements possible. There is no rotation possible here. There is no translation along the y-axis possible. There is no translation along the x-axis possible. Now, if we come to this roller support, we know that a roller support will not allow the beam at this end to translate downward. It will not allow to translate downward. Also, it will allow this beam to rotate at this end. It will allow this beam to rotate at this end. So, as there is no axial load applied in this beam, so we simply ignore the axial deformations. We ignore the axial deformations, and if we ignore the axial deformations, it means that we are ignoring the translating along the x-axis of this of the beam at this support. So what we are left with, the only deformation, the only displacement we are left with, is this rotation at this joint B. This rotation, okay. So this rotation, you know that this rotation is called theta. It is always denoted by theta. So this is a theta B, which is the rotation at this support. So now the only unknown we are left with in this problem is this theta B. Why it is the only unknown, and why we are taking displacement as the unknown? Because we have stated earlier that the unknowns in case of the stiffness method will be the joint displacements. So now, as compared to the flexibility method, where the unknowns were the actions, were the redundant actions. So now we will be taking this theta B as the unknown in our structure, and we will be then carrying out some steps to find out the value of this theta B. Once the value of this theta B is found out, then we can incorporate this value in some equations, and we can then solve the whole structure with the help of this value of theta B. So now we proceed further. Okay, so now in the second step, we obtain a kinematically determinate structure. A kinematically determinate structure by what? By altering the actual structure in such a manner that all unknown displacements are 0. Now we are required that we change the actual given structure in such a way that the displacement at all the joints becomes 0. It means that the structure has no, then the structure has no such joint where any kind of displacement is possible. So currently we know that we have one support as a fixed support, the other is a roller support, in which we are ignoring the axial deformation, so we are left only with the rotations. So we have only one rotation which is unknown. So we now need to change the actual structure such that the value of theta b is equal to 0. How we will be doing this? So now we'll be looking at it. Okay, so what we were doing in the flexibility method in this step, if you remember, in the flexibility method, we were doing in the same. What we were doing, we were actually obtaining a statically determinate structure, or which we also call the release structure, and we obtain this structure by altering the actual structure in such a way that the selected redundant actions are 0. If you remember, the first step was to select the redundant actions, and then in the next step we released those actions so that their values were 0, and then by doing so we got a structure which we call as released structure, or a statically determinate structure, if you remember. So now in the stiffness method, we will be we will be changing the actual structure in such a way that the displacements are 0, and we obtain a kinematically determinate structure. I hope this is clear. Okay. Since the unknown displacements are translations, translation along the x, translation along the y, and rotations, okay, for 2D there will be only one rotation. Okay, there's a question from one of the students. So he's asking that there is a translation possible at V, and why we are not. So I just told you that we are ignoring the axial deformations, and we are considering the beam to be axially very stiff. Okay, we are considering the beam to be axially very stiff, and that's why we are ignoring the axial deformations. Also, if you look at the beam on the previous slide, there was no axial force applied. So due to which the axial, if you even consider the axial deformations and you find out the value at the end, so that will be so small that you will feel that I should have ignored that earlier, because by considering that there will be many calculations involved. Then you will have to calculate that you have to then consider that translation along the x in many steps. So as we know that at the end we will be getting the value so small, very near to 0. That's why we take that equal to 0 at the beginning, so that our calculations are relatively easier later. Okay, so now the unknown displacements are the translations and the rotations of the joints. So how can we make these translations and rotations equal to 0? We can make them equal to 0 by restraining the joints of the structure against displacements of any kind. Okay, so we should now restrain the joint against any displacement. So by restraining the joints against all the possible displacements, the structure we obtain, we call it now a restrained structure. We call it now a restraint. You should now be getting familiar with these terminologies. We were using earlier in the flexibility method, we were using a release structure, if you remember. And there is a difference, clear difference. In the release structure, we are making the selected redundant actions equal to 0. And here we are making the joint displacements equal to 0. So there is a clear difference. Okay, so now the structure we obtain, we will be calling it a restraint structure. So let's see how we can make this example beam equal to a restraint structure. Now it is not a restraint structure because we know that at this joint there is a rotation, which is theta b. So now we want to change this beam in such a way that this theta b is equal to 0. How can we do this? we simply need to change this support at B from this roller support to a fixed support. Let's see this. This is the beam. So if we remove this, this roller, and we replace this by a fixed support, so now this becomes a beam in which there are no displacements possible at the joints. There is zero displacement possible at A, there is zero displacement possible at B. So now this become our restrained structure. This now become our restrained structure, okay? So once you fix this, now we can see that this theta B is not possible, and now the deflection will only be at the middle of this beam, and away from, it will start at a point away from these joints, and it will be maximum at the center. So now this is what we call our restraint structure. This is what we call our restraint structure. I hope everything is going clear for you. Okay. Now, can you tell me that what will happen if this restraint structure is acted upon by the given load? We know that we have given in the very actual structure, we were given this load W, a uniformly distributed load, that it is acting on this beam. And now we don't have this roller here because we have changed this roller to a fixed end, because it is the requirement of stiffness method that in the after selecting the after finding out the number of possible displacements, you need to make those displacements equal to 0. So the only choice we were having to make this theta B equal to 0 is to replace this joint by a fixed joint. Okay, so now here there is no theta B possible. So now if this W acts on this uniformly distributed load acts on this structure, what will happen? Okay, you know that this will create a moment at this end, a resisting moment at A, and also a resisting moment at B. But we will not be focusing on the moment at A, because we know that this fixed end was there in the original structure. Rather, we will be focusing on the moment at B. Why? Because this is the end which we changed. We changed this end from the roller to a fixed end. So now we will be focusing on this joint. Okay, our whole focus in these steps will be on this joint. So when this W is applied, this uniformly distributed load of magnitude W, this will create a moment MB. You can see here, this will result in a resistive moment, a reactive moment MB. Okay, and this reactive moment will be in the clockwise direction, and the magnitude will be given by this uniformly distributed load multiplied with the square of the length of the beam and divided by 12. So it means that in the original structure, you have to be very carefully listening now what I'm saying here. If you remember, in the original structure, there was no this moment possible because there was a roller support. So even if the load acts here, so the roller cannot resist a moment. So the resistive moment at the roller support will be 0. It means that it is due to our altering of the beam, due to which this MB has been created here. Okay, it means that we have created this MB a kind of through our own decision. Okay, there was no MB in the original structure, but we changed the beam such that now we are getting some value of mb, and the value of mb is equal to wl squared over 12. Now, you know that in mathematics, when you are changing an equation, for example, if you are adding some number to one side of the equation, so it is the rule, it is a very general rule that you have then to add the same number on the other side of the equation, else your mathematics will be wrong. So here we have changed the structure such that we have introduced a value of mb, and this value of mb is acting clockwise because this w will be acting in this direction, so the resisting moment will be coming in this clockwise direction. So now we should again change or alter the actual structure or the restraint structure such that this value of mb, this introduction of the value of mb is compensated. By compensation, I mean that we should do such things that both sides of the equations are equal, so that if we are adding this mb, in the next step we should now be subtracting this mb, because this is a general mathematics rule that if you are adding something, you should subtract the same thing. Okay, now let's see in the next step. Before going to that, let me clear some more things here in this step. We will be going to that in the on the next slide. So let's discuss some more things here. This moment mb, it is an action, and this action is corresponding to the rotation theta b. A very important statement here, very important statement I have written. I'm saying that this moment mb, it is corresponding to the rotation. Here, if you remember, here was a rotation theta b. I'm saying that this moment mb is corresponding to rotation theta b. What do we mean by this? We mean that in the original structure, there was a theta b. Let's say for example, the theta b value is equal to 15. The theta b value is equal to 15. This is just an arbitrary value I'm choosing here. So it means that if the value of mb is equal to 0, the value of theta b will be the same 15 units. If you increase this moment, if you increase this reactive moment mb value in this clockwise direction, it means that now this joint was rotating, and in this direction it was rotating, and you have now resisted that rotation by applying a resistive moment. It means that this rotation will now decrease. Now if I further increase the value of mb, it means that the value of theta b will approach 0. Why? Because this moment is actually resisting the rotation at this end. I hope this is clear. Okay, that's why I'm saying that the action corresponding to theta b is moment. But a very clear terminology here. Action. I'm saying action, and I'm saying rotation. So action means force. Rotation means displacement. So this is a force. This mb is a force corresponding to a displacement. So you know that a displacement can be resisted by a force. So if you look at this joint, if there is no resistive force applied at this joint, so this joint will rotate very easily. But if you apply some resistive force means if you resist this rotation here, so then the rotation will be reduced. Okay. So now, as I have told you that this is also a stepwise procedure. So we will be denoting such action. We will be denoting such action by ADL matrix. Later on, you will see you will be using ADL matrix again and again. So you should remember that from where this ADL matrix is coming. This ADL matrix is actually this resistive action, which is coming from the actual load. When actual load is applied on the strain structure, and the moment obtained in such structure, we will be calling it as ADL matrix. Now, this is exactly what I told you in that discussion, that because there is no moment possible at the joint B in the original structure, and we have changed that structure such that there is now a moment MB possible due to the applied load. Here in this step, we change this original structure, we change this joint by a fixed joint, and now a moment MB is possible. We can see there is the moment MB now coming. So it is a rule of mathematics that if we are altering this actual structure such that we are getting a value of MB, so now we should alter this structure such that the same MB value should be subtracted. Okay, so there is addition and subtraction. So now what we do, we now next consider a restrained beam which is subjected to a moment equal and opposite to the moment MB. So now in the next, we now consider same restraint structure, the same restraint structure, but now it will be acted upon by a moment MB, which is exactly in the same magnitude as this moment MB. Here, as we have introduced this MB, so now in the next step, we will be doing such that the same MB value is compensated. So in the next, now we apply the same moment, but in the opposite direction. Now you can see that this is anti-clockwise. Here the moment is clockwise, and here the moment is anti-clockwise. Okay, what will be the effect of this applied moment here? If we apply a moment here at this support B, so what will be the effect? See this. You are rotating a joint by a magnitude MB. So in the originally, this was the support. If you are looking at this, this is the support. But when a moment MB is applied, so this support will rotate. Depending on the magnitude of MB, which is coming from this theta B, so this support will rotate. So here I have shown the rotated support. This now have rotated. So it means that if we rotate this, it means this rotation is now disturbing the whole beam, especially this area, and it is now again producing some rotation, because we know when the joint is rotated, it means the joint is at this end, it means the beam at this end now will be rotated. This moment will now be creating theta B. Okay, so the summary is, this is the original structure. We change the original structure such that no displacement is possible. We got MB. As per the general rules, if you are adding something, you should be subtracting the same thing. So now we have applied the same moment in the opposite direction, and this moment has now created a theta B in this structure. Okay. When the actions acting on the two beams are superimposed, they produce the actions on the actual beam. So now if you add these two situations, it will exactly result in the original structure. How this will be possible? Let's see this. This is the restraint structure. This is the restraint structure. When we add this to this structure, there is some problem in these slides. What we did initially, we changed the support type such that there is a moment MB coming, and then we applied a moment MB. So if we add these two situations, so what will happen? This MB will be cancelled out with this MB, and we will get the original structure. This theta B, and now this original support, because this moment has now been cancelled by this MB. It means now why I'm showing this thing to you. I'm showing it because I want to tell you that if I'm changing the beam, so the changing in the beam is according to the mathematics rules, or according to the general rules which we follow generally in mathematics and for equations. So it means I'm not doing any such things which are against the rules of the mathematics. If I'm adding something, I'm subtracting that thing, and if you if you add these two things, so the net result is the same as was given to us. Okay, so far I have not changed any support such that it produced a permanent change. Okay, there is no permanent change produced so far. If you add these two situations, it will be exactly the same as the original situation. So now let me change again this presentation to the original. Okay, so I hope it is now clear to you. Okay, now we proceed further, and we now introduce a concept, and that concept is of the stiffness method. If we consider a spring, and this spring is acted upon by an action, and under this action, this spring is displaced by D. We already studied this in the flexibility method, if you remember. This spring is displaced by a distance D under the action A from this point to this point. Okay. So now, how can we relate this action and this displacement? So if we relate this, we can say that the action is directly proportional to the displacement. This action is directly proportional to displacement. It means the more this displacement, the more will be this action. Okay. So if you displaced this spring, by a distance 2d equal to 2d, and then you release that, so the restoring action, this action, then it will be equal to 2a. It means that this action is actually proportional to this displacement. The more this displacement, the more will be this action in the spring. So it means that A is proportional to displacement. So if we replace the proportionality sign by the equality sign, so we will have to introduce a constant, and this constant is equal to S. And this S shows the stiffness. It shows the property of the spring, which we call stiffness. Okay, it means that the the action, this action depends on the displacement. So if we only write that the action is depending on the displacement and we don't write this S, so what will happen? Now if I change this spring, this is a thin spring, a small spring, let's say, and then I change this spring by another spring, which is a very thick kind of, which is made of a very thick kind of dimensions, and of different stiff material. So now what will happen there? Will the action be now the same? Now if I displace this spring by D and I displace that spring by D, so what do you think? Will this action be the same in both type of springs? Any comment? No. Why no? Because the one spring has different property than the other spring due to its dimensions, due to its material. So and that property which is making the difference, we call that property as stiffness. So it means that if the more the stiffness, so then there will be this more action there. Okay, so because more force, you know, if this is a stiff spring, so there will be required a more force to stretch the spring. So as compared to a spring which has a less stiffness. Okay, so it means that the action is equal to the stiffness times d, and this stiffness is the material property, it is the spring property here. Okay, now I hope this is clear. So it means that if we separate the stiffness S, so this will become equal to the A divided by D. It means that now we can define stiffness as the action produced by a unit displacement. This is how we define the stiffness. It is defined as the action which is required or which is produced by a unit displacement, or we can define it as it is the action required to produce a unit displacement. So what quantity of action is required to produce a unit displacement, or if we apply a unit displacement, then that unit displacement will produce how much action. This is the definition of the stiffness. So we can apply the same concept of the stiffness to the structures. Now let's see this. How can we apply that? Okay. This is the situation we discussed earlier, but now I have changed the capital MB by a small mb, and now I have changed this theta b, and I have chosen theta b to be equal to 1. Okay, in the previous there was capital MB involved here. Now we have a small mb, we have represented it by a small mb, and this small mb is not equal to the capital MB. Remember, I'm now introducing the concept of stiffness here. That's why I'm doing this. Okay, so this theta b is the displacement. It is the d value, d, and the action produced by this displacement is, we know that the moment is the action corresponding to rotation. So the action corresponding to this displacement is this moment, which we are representing by mb. It means that if what is stiffness S? S is equal to what? A divided by D. So in this case, action is equal to this moment mb, small mb, and this D is equal to this theta b, this rotation. So now if I know that stiffness is the action produced by a unit displacement. That's why I have chosen this displacement to be 1. And if I rotate this beam by a value of 1, then the corresponding action, which is unknown, it is denoted by mb, and I can call this mb as the stiffness, because why? This is the action produced by the unit displacement. So this mb now becomes my stiffness, as it is corresponding to the unit value of displacement. Okay, and what will be the value of this small mb? The small mb, we know that, you know, from the analysis 1 course, that this mb and this theta can be related by this equation, 4ei over L into this rotation. And we know that in this case, this theta b is equal to 1. So this becomes mb becomes 4ei over L. And I'm calling this mb as a stiffness coefficient. Why I'm calling this as a stiffness coefficient? Because we know by the definition we introduced on the previous slide, we know that the stiffness is the action produced by unit displacement. So this is the unit displacement and this is the action produced. So this mb becomes our stiffness coefficient, and the value of this stiffness coefficient will be equal to 4ei over L. 4ei over L. Okay. Now, if you remember, this is all what I have discussed here. So you can have a look at this. This mb now becomes our stiffness coefficient. And the corresponding matrix we obtain, we will be calling that as the stiffness coefficient matrix. And we will denote that by S, stiffness coefficient matrix. What it will include? It will include all those corresponding action values which are coming from the value of unit displacement. So here the only unknown in this beam was this theta b. So if I equate the theta b to 1, so the value of mb I get is the stiffness coefficient, okay, and which is given by 4ei over L. Now let's go back and let's see what changes are now be made here. In the earlier discussion, we were discussing that we should, if we introduce mb in this direction, we should introduce another mb in this direction, so that their effect is the same as the original structure. But what we did here, we introduced this mb, capital MB, but now we have introduced the concept of the stiffness method, the stiffness, and we took this displacement equal to 1, due to which there is a moment coming which is small mb, and this small mb is not equal to this capital MB. It means that the joint equilibrium equation, or the equation of action superposition, now we have to make some changes here. We have now to make some further changes, and we should now pick some value from this structure. From this structure, we should pick that value which is equal to this value, but opposite in direction, so that we get 0 here. So what value we can get from there? Now this is very important here. You should now be very carefully listening here. What I did here, if I'm saying that for, if the value of theta is equal to 1, if theta is equal to 1, then the action is equal to mb. Listen very carefully. I'm saying if the displacement is equal to 1, the action is small mb. Now, what will be the value of the action if the value of displacement is theta b? सिंपल अल्फाज में अगर थीटा की वैल्यू 1 हो तो डिस्प्लेसमेंट तो मोमेंट एम बी होगा. तो अगर थीटा की वैल्यू थीटा बी हो जाए तो फिर यहां पे मोमेंट क्या होगा? It is the same as if I say that if 1 kilometer is equal to 1000 meters, if 1 kilometer is equal to 1000 meters, what will be the value of 4 kilometers? What will be the value of 4 kilometers? G. If the value of 1 kilometer is 1000 meters, what will be the value of 4 kilometers? Simply multiply this 4, simply multiply this 4 with the value coming from the unit kilometer. So from the unit kilometer, the value is coming 1000. So multiply this 4 with this 1000. It means that here the capital MB value will be equal to, the capital MB value will be equal to this value which is coming from one value of displacement, so that is small mb, times what? Times theta b. Times theta b. I'm sorry for this writing to be so bad because I'm using the mouse, but if you are going along my discussion, so you can understand even if I'm not writing clear here. So I hope now this is clear. I hope this is clear. Why it will be equal to capital MB? Because this capital MB, we already said that this capital MB is equal to theta B. Initially, very start में मैंने आपको कहा था, in the very start I told you that this MB will be exactly equal to this theta B. Okay, so it means that if we apply this MB in this direction, now from this structure we should get a value of MB in the opposite direction. So that value of MB now we are representing in terms of stiffness. In terms of stiffness, that's why we are calling it stiffness method, because we are using the stiffness concept here. So this MB times this theta B, this gives us the total MB here. Now if we apply the equation of action superposition, this equation of action superposition, it is also called the equation of joint equilibrium. It is also called the equation of joint equilibrium. It means that if we add the situations at this joint B, so what we will get? We will get the situation in the original structure. So if you see here, this is the capital MB. It is coming from this situation. And now this MB theta B situation is coming from this situation. And now if we equate them as they are equal in magnitudes and opposite direction, so it will give us 0. It will give us 0 moment at this support, which is actually 0 in the original structure. So now this is all correct for us. We have introduced the stiffness procedure here, and we have equated this equation. This is capital MB, this is small mb. Now, if you remember, earlier in the earlier step, this capital MB, we also called it ADL, if you remember. We also called it ADL matrix. And this small mb, which I am calling my stiffness, so I can also show it by the stiffness matrix, as I am doing it here. So now if I replace this mb by the ADL, and if I replace this mb by this S, and this theta is actually the displacement. This theta is this displacement. So I represent this by this D. I represent this by this D. And what is this AD? This AD is the action corresponding to this displacement D, which is in the original structure. यहाँ पे ये, this one. This is the AD in the original structure. This is called AD. So this, it means that if you add ADL, which is this capital MB, plus the MB times theta B, which is the stiffness, so you get ADL, which is the moment in the original structure. So we know that in the original structure the support is roller. That's why the moment there will be 0. So it means that now the, according to the action principle of the superposition, action superposition, we obtain this equation, and I have explained this equation also. If you have any problem in this, I can re-explain this. Quickly tell me, so that then we proceed. I have explained all these terms here very clearly. Here, AD, ADL, DS, I have explained them here. So let's find out the value of D. This is the equation we will be using to find out the value of D. What is the value of AD? The value of AD is 0. Why it is 0? Because AD is the action corresponding to displacement. The unknown displacement is theta B, and the action corresponding to this theta B is the moment M, which is 0 in this case, in the original structure. So we give it a name AD. So AD is 0. What about the ADL? From where the ADL value is coming? The ADL value is coming from this MB. When the restraint structure is acted upon by the actually applied load. So the value of this is equal to WL square over 12. You know, we have written this on one of the slides. Okay, this is the fixed in moment, WL square over 12. And it is in the, we are taking clockwise moment as positive, okay? This is a clockwise moment. This will be taken as positive. And what is stiffness S? It is equal to small mb. And what is small mb? It is 4 ei theta over L, but theta is equal to 1, so it becomes 4 ei over L. And what is D? D is equal to this theta B, which is unknown. So if we put these values, 4 ei over L is the stiffness. So we take stiffness inverse times AD. AD is this value, it is 0, minus ADL, which is WL square over 12. So what we get? We get, if you simplify this, we get D to be equal to WL cube over 48 EI. With the negative sign, and this negative sign is showing that the rotation, the direction of theta is anti-clockwise, because clockwise is positive and this is negative. It means theta B is anti-clockwise. That's how we find the value of D. And once the value of D is known to us, then we can put this value of D, capital D, in some other equations, which we will be discussing in example problems, to solve the whole structure. So this was about the introduction to stiffness method, and this, I hope this is clear why it is called stiffness method, from where we introduced the stiffness concept, and how we then applied the action of superposition and how we got that equation. So I hope all this clear to you. You just think over it, and now we go to introduce this kinematic indeterminacy, and then we will be solving a problem. So now solving a problem will not be a big issue, because we have just introduced all these concepts. So I don't think that it will now be an issue. So now we will be clearing some more concepts there also in the example problem. But before going there, let's quickly go through this kinematic indeterminacy. Kinematic indeterminacy of this fixed support, it is equal to 0. Why? Because we know that kinematic indeterminacy, it is giving us the degree of freedom of a structure, and we know that a fixed support don't allow translation, nor it is allowing rotation, which means kinematic indeterminacy at a fixed support will be 0. And if there is a hinged support, then the kinematic indeterminacy will be equal to 1 degree, because we know that the only degree of freedom it is allowing, it is that rotation. And it is 2 degree in case of a roller support, if you are not ignoring the axial deformations. If you are ignoring the axial deformations, then the hinged support and roller support have the same degree of freedom. Okay, so now let's quickly do an example on this. If you want to formulate through some formula, so this is 3j minus r plus I. This j is actually the number of joints, so 1, 2, number of joints here. R is the number of reactions, 3 reactions here, 1 reaction here. And I is the number of internal hinges. So if there is 1 hinge, then I will be equal to 1. If there are 2 internal hinges, then I will be equal to 2. Let's solve this problem. This is now in this beam, if you see, the j number of joints are 2, this 1 and this 2. So this will become 3 times 2 minus reactions. How many reactions? 3 at this support and 1 at this support. So 3 plus 1, this becomes 4. And how many internal hinges we have in this beam? We have 0 internal hinge here. It means it is 0. So if you find out the value of Ki from this one, so this is 3 times 2 is 6 minus 4 is 2. So I hope this is very clear to you. So now let's do an example problem on this.